Is a mathematical game with 3 poles and a given number of disks of diminishing size, where the goal is to transfer an entire stack of disks from one pole to another, to either of the 2 vacant poles, where disks are moved individually and no disk may be placed on top of a smaller one. Placing the smallest disk here and then placing a medium disk on top of it is considered an illegal move. So before connecting this to Pascal's Triangle, we'll play the game with a small number of disks, 3, labeling them as follows: disk 1, disk 2, disk 3. We first move disk 3 once, disk 2 once, disk 3 for the second time, and disk 1 for the first time, disk 3 for the third time, disk 2 for the second, and disk 1 for the fourth and final time. We've successfully finished the game in the minimum number of moves required for 3 disks. 1 plus 2 plus 4, or 7 moves. We can recognize this diagram. We isolate the numbers 1, 1, 1, 1, 2, 1. We find the number of times disk 1 is moved, the largest disk, is given by 1. The number of times disk 2 is moved is given by 1 plus 1, or 2. The number of times disk 3 is moved is given by 1 plus 2 plus 1, 4. We notice that this diagram is actually the selection of the first 3 rows in Pascal's Triangle. Based on this, we can generalize that the minimum number of moves required for n disks is equal to the sum of the elements in the first n rows. So as the disks approach and larger sums are involved, we can make use of the row sums pattern explained before. For 3 disks, we have 2 to the 0th power plus 2 to the first plus 2 squared, giving us the sum of all the elements in the first n rows. This geometric progression, it's called, by a factor of 2, is given by the formula mn, or moves for n disks, equals 2 to the nth power minus 1. Substituting n with 3, we have m3 equals 2 cubed minus 1, 8 minus 1, or 7. With this connection between Pascal's Triangle and Tower of Hanoi, we can approach the game with 4 disks. Logically, we find it is only a matter of moving the top 3 disks, one at a time, to another pole, occupying 7 moves, and then moving the largest disk once to a new pole. We then only have to move these top 3 disks with 7 moves again, individually, to the top disk, as if the bottom disk does not exist. So, this logical explanation can be summarized in the formula, or recurrence relation: n plus 1, or moves from n plus 1 disks, equals 2 times the moves for n disks, or in here it was moves for 4 disks equals 2 times the moves for 3 disks, plus 1. So, calculating the minimum number of moves for 4 disks in terms of 3, we have m4 equals 2 times mn, which we know from m3, which we know from before is 7 moves, so 2 times 7 moves is 14, plus 1, 15 moves. If we substituted 4 into the explicit formula, we would receive the same answer. And this relationship between the disks, the explicit formula for n disks, and the recursive formula for n plus 1 disks is shown here in the table. Sierpinski's triangle. Sierpinski's triangle is a unique shape, a geometric shape with some unusual properties. It is formed as follows. We first blacken a triangle. We then plot the midpoints, plot the vertices of a smaller white triangle at the midpoints of a larger. We notice 3 new black triangles are created. We repeat the process, dividing these new black triangles with white triangles. Here, here, and here. And as I do this, we notice that even still more black triangles are produced. We repeat the process again. Filling these black triangles, dividing them with white ones, more are produced. And after I finish this, we'll see that, or if this is repeated infinitely,